Welcome to my presentation on expressivity and complexity of linear time temporal logic with Team Semantics. And this is joint work with Jana, Bernd, Juha, and Fan. And here you can see their affiliations. So what is the basic setting for verification and specification of concurrent systems and logics therein? Well, the idea is that take your system, for example, a piece of software or hardware, and construct from it a crypto structure that depicts the behavior of the system. Then a single run of the system is depicted as a trace generated by the crypto structure. And then properties of the system, such as every request is eventually granted, can be written as a formula of some formal language that expresses the property. And then there are two basic decision problems related to this setting, which are the value checking problem and satisfiability checking. So in the first, you are giving a system and a specification, and you want to know whether the system satisfies the specification, or in the logical term, whether the structure satisfies the formula. And in the SAT solving, you are giving a specification or a collection of properties, and what you want to know is whether the specification can be realized. So whether there exists a model that satisfies the formula that you are given. Okay, so there are of course many logics in the literature for both trace properties and hyperproperties of systems, but the trace properties have been more studied on for a long period of time already. So trace property is really a property of traces. So for example, a property that says that each request is eventually granted. So then a system satisfies a trace property if every trace of the system satisfies it. But not all interesting properties are such kind of properties. So for example, the property each request is granted in some bounded time is not a property of traces, but it's really a property of sets of traces. And these kind of properties are called hyperproperties, and the logics of those are often called hyperlogics. So you have, for example, HyperLTL, which is designed to define properties of hyperproperties of systems. Well, the common hyperlogics like HyperLTL, HyperQPT, and whatnot are essentially extensions of LTL, QPT, and whatnot with trace quantifiers. And with this kind of quantifiers, you get high complexity or often undecidability. And they also have the defect that they are not really well suited for properties involving unbounded number of traces. So I will come back to that a bit later. So what do we do in this paper is that we advocate the use of team semantics for temporal logics that express hyperproperties. So the idea there is that the team semantics is a framework that is directly designed to define properties of sets of things like hyperproperties. And also logics that come from that direction do not change the baseline logics. For example, TeamLTL is still a pure modal logic, while HyperLTL is not. So what do we do here is that we study the expressivity and complexity of different logics. So we relate the expressivity of variants of TeamLTL to variants of hyperlogics, and then we study the complexity of TeamLTL and try to explore the undecidability frontier of TeamLTL. And indeed, we discover large fragments of these logics that are decidable, but we are also, on the other side, able to show that if we extend TeamLTL with inclusion atoms and Boolean disjunctions, we get already undecidable logics. So what we do here is to try to pinpoint exactly where we go from decidable to undecidable. Okay, so this is a common problem when you come back to office from a holiday or even from working from home during COVID. So you come to your office and you find your computer shut and you want to get it ready. So this is a very simple crypto structure that depicts the situation. So on the other side, you might be able to get it loading directly and then your computer is ready. Or your university might be such that you need to connect to all kinds of online systems and the connecting might take forever or a long time at least. So if we think this as a root of our crypto structure, then it generates this kind of infinite set of traces depicting all the possible ways of your system to evolve. And now like I mentioned before, trace properties are properties of traces, and a system satisfies trace property if every trace has the property. For example, the computer will eventually be ready is such a property, so you can check each trace in isolation whether this is true on the system. On the other hand, hyperproperties are properties of sets of traces. So for example, here, the property that the computer will be ready in a bounded time. It is not a property that you can check by checking each trace one by one. So for example, if we take all the traces here, except the one that stays here forever, it will not satisfy the property that the computer will be ready in bounded time, even though every trace there satisfies the property. And for example, if we take only these 3 traces here, then this satisfies the property that the computer will be ready in bounded time. Linear temporal logic is one of the most prominent logics for specification and verification of different systems. Indeed, there are model checking tools that in the industrial context routinely and automatically verify whether a system satisfies its LTL specification. But what is the reason for the success of LTL, for example, over first-order logic? Well, one thing is that LTL is a purely modal logic, and that gives it many desirable properties. So for example, LTL is decidable, and the complexity bounds are not that bad. So for example, the model checking and stability problems are piecewise complete, where for example, the 2-variable first-order logic and 3-variable first-order logic are already either next time complete or even non-elementary. So LTL is a very good logic, but the caveat here is that LTL can only specify trace properties, and we are interested also here in hyperproperties. So a basic recipe for logic for hyperproperties is just take a logic for trace properties and add trace quantifiers. Like here, for example, we take LTL, where the satisfying object is a trace, and then we add quantifiers for the traces, and then we get a HyperLTL. So here you can see that the satisfying object here is a set of traces T and a trace assignment. And then we can also take an hyperextension of QPTL. So we add uniform quantification of propositions to HyperLTL. So there are many logics already for hyperproperties, like I mentioned, this quantification-based HyperLTL and HyperCTL. And these do retain some interesting and desirable properties of LTL, but these are not purely modal logics. It seems like you saw from the last page, they really had these kind of trace quantifiers that have this kind of first-order flavor. So the existential fragment of HyperLTL is still in p-space, but the full logic is already non-elementary. And for satisfiability, it's already highly undecidable. And it also has this defect, or that it can only define properties using fixed finite number of traces. Essentially, you have quantifiers for the traces, and all properties that you can define with the formula, then just talk about those traces that happen to be quantified by your variables. So for example, bounded termination is not definable in HyperQPTL. So now the idea that we have here is that team semantics is a very good candidate as a purely modal logic to define hyperproperties of systems without some of the caveats of HyperLTL. Okay, so what is the basic setting of team semantics? Well, in most logics, formulae are evaluated with respect to single states of affairs. So first-order logic, you have your first-order assignment. In propositional logic, you have your propositional assignment, and in modal logic, you define your formulae with respect to pointed Kripke structures. So this all can be lifted to team semantics, where the idea is just to replace these single state of affairs to sets of states of affairs. So in first-order logic, formulae are evaluated with respect to sets of first-order assignments, and in modal logic, over sets of possible worlds. And these sets are then called teams. So here is a short historical picture on the development of team semantics. So the idea of team semantics can be traced back to Hodges, where he built a compositional semantics for the IF logic of Hintikka and Sandu, which again can be seen as a linearization of branching quantifiers by Henkin. But the real starting point of the endeavor of logic with team semantics can be traced from the works of Jouko Väänänen from the early 2000s, from his definition of dependence logic. And after that, there's been a lot of activity in this area, and there's been numerous variants that have been defined, like model dependence logic, inclusion logic, independence logic. Probabilistic teams have been considered, and now also TeamLTL, so team semantics in the temporal logic setting. So what is TeamLTL then? Well, from the point of view of the syntax, we get the same syntax as in LTL, but the formulae are evaluated directly on sets of traces. So in LTL, the satisfying object is a trace, but in team semantics, the satisfying object is a set of traces. And we just use this time step here as a convenience. And now the crucial thing in team semantics is that it allows us to add new atomic statements on the logic. So since our logics are really defined on sets of traces, we can think what kind of hyperproperties we want to be able to express in our logic, and then we can add those properties as atomic statements and then build a logic around those. So this is a really flexible setting in that sense that you can start with the atomic propositions statements that you are interested in and then build a logic around that. And then you can also, depending on what you want to be able to express, add additional connectives to your language. So these kind of extensions are a well-defined way to delineate the expressivity and complexity of logics in this setting. Okay, so temporal team semantics is universal and synchronous. So what do you mean by universal? Well, the point is that what do you mean if you're saying that a set of things satisfies a proposition P? Well, certainly what you are saying that every trace in the team satisfies the property. Likewise, a set of things satisfies negation P if every trace in the set satisfies negation P. So that is the universality of TeamLTL. Well, the synchronicity is defined as this. So we have a single time step with respect to the set of traces. So the set of traces T at time step I satisfies future phi if at some future time step j, Tj satisfies phi. And likewise, Ti satisfies it's always going to be phi if Tj satisfies phi for all j larger than I. So here's an example of this. A property stating that there is a time point common for all traces after which A does not occur. So it's not expressible in HyperLTL, but it can be expressed in HyperQPTL and indeed also in TeamLTL. And here you can see that there are indeed these kind of properties that are very nicely definable in TeamLTL, but in this HyperQPTL setting, the formula is already quite complex. So how is this expressed in HyperLTL? Well, there is a time point common for all traces after which A does not occur. Well, the time point can be now expressed with existence of a P. Because in HyperQPTL, what we wanted was that the P needs to be uniform. So in the quantification of P, we have to give it a value so that it is true here if and only if it's true here. So now you can see that if you color your trace like this, then you can use the P as an indicator of the common time step. And then we just say that for all pi's, P is in the future, and if we go to P, then everywhere after that, it holds that A is false. But using this synchronous TeamLTL, this can be said by just saying in the future, it's always going to be that A is false. So here we have a team here satisfying in the future, it's always going to be that A is false, because here there is a time step in the future here, where it holds that it's always going to be in the future that A is false. In team semantics, the disjunction is defined a bit differently than you might think first, but it is very natural. Because what does it mean that a set of things satisfies a disjunction, let's say phi of psi? So for example, you have Christmas presents that are blue or red. What you are really meaning is not that all the presents are blue or all the presents are red, but you are saying that some of the presents are blue and some of the presents are red, and there's no other presents. So indeed, a set satisfies a disjunction if you can decompose the set into two subsets that cover the the original set satisfying the disjunction. So indeed, this is how we now interpret disjunction. So Ti satisfies a disjunction if there exists a partition of the team satisfying the disjunction. The conjunction is classical. And here is an example of a similar properties defined in HyperLTL and TeamLTL. Here in HyperLTL, this formula says that for all pairs of traces, pi and pi prime, it holds that there is a time point in the future such that either A is true on both of the traces or B is true on both the traces. For example, if we pick this and that, we find that here B is true here and B is true here. But in TeamLTL, like I said, the disjunction is a bit different. So this future A or future B says that we can split the team into two parts such that there exists a time point in the future in the first part where all the traces satisfy A, and also in the second part you have a point common on all traces in the future where B holds. But of course, either one of these sides could also be empty. Then we have the dependence atom, which states the functional dependence between variables. So a team satisfies the statement that P1 to Pm functionally determine Q if it's the case that if we take any two traces from the team that agree on P1 to Pm, they must also agree on the truth value of Q. And then we can express this kind of complex statements like non-deterministic dependence, where an output either depends on an input 1 or an input 2. So this formula says that you can split the set of traces into two, where on the other side, if the traces agree on I1, they must agree on O, and on the other side, if they agree on I2, they must agree on O. And instead of dependence atoms, we could also express the same dependence by going through all the possible alternatives by using a Boolean disjunction. So here is another example which states that depending on an unknown input, execution traces either agree on A or they agree on B. And now this can be expressed in both HyperLTL or TeamLTL. And again, you can see the difference of how these things are said in these two settings. And finally, we have inclusion atoms. But the point is that these state the inclusion of truth values. So this is true here if every truth value that occurs in some assignment for P1 to Pn also occur as truth values for Q1 and Qn by some trace in T. So it says that for every trace T, there is a trace T prime such that the Qi's get the truth values of Pi's to T prime from T. And using these inclusion atoms, we can express many different kinds of properties. For example, all trace properties can be expressed in TeamLTL using these. So for example, this formula says that phi gets only true values in T. So it's exactly the same as for all pi, phi holds. Likewise, this says that there exists a trace in the team where phi is true. So there are also some properties involving single quantifier blocks that can be expressed in TeamLTL, but this is a bit more involved question, and this does not always hold. But for some properties where essentially the properties have some kind of permutation invariance property, we can write a complex formulae of TeamLTL defining these. And when we go to quantifier alternation, it becomes even more trickier, and there really is no direct way of mimicking quantifier alternation in this TeamLTL setting. Okay, so here you can see the semantics of TeamLTL, and this is the syntax of the basic logic. So we have conjunction, disjunction, next, until, and weak until, and these until and weak until are defined as you would guess. So Ti satisfies phi until psi if there exists some time step k larger than I where tk satisfies psi, and everywhere between tm satisfies phi. And we can of course define these future operators and globally operators in a normal way using until and weak until. we use this notation to denote the extensions of TeamLTL with the atoms and extra connectives in the brackets. Good. So what is the motivation of our work here? Well, essentially, it is to develop purely modal logics for hyperproperties. And why is that? Because we want to discover decidable and expressive logics. And often modal logics are such that they give a good balance between expressivity and complexity. And then we want to investigate connections between the settings of HyperLTL and TeamLTL and their variants. Okay, so let's see a bit of our results. So the final technical thing that we need is the concept of a generalized atom. So we have described dependence atoms, inclusion atoms, and whatnot, and those are just special cases of this general phenomena of a generalized atom. So you can just think B as a second order truth table. So essentially, it's a truth table for atomic hyperproperties. And this kind of construction just allows you to take any atomic hyperproperty and make an atom out of it. And then you can feed LTL formulae in it, and then you have these semantics. But essentially, the thing is that this is exactly like the inclusion atoms or dependence atoms that we expressed earlier. The truth condition is just given this is given by this second order truth table instead of the formula that we write above. And now the nice thing is that we get these nice representative logics. So if we add in this TeamLTL Boolean disjunction that we described earlier, and then these two constructions, so an atom that states that the team is non-empty, and then this kind of flat operator, which is defined like this. So Ti satisfies flat op phi if every singleton in the team satisfies phi. So if we add these constructions, we can express all generalized atoms. And if we only put this Boolean disjunction and flat op, then we can express all downwards closed generalized atoms. And the nice thing here is that this logic itself is a downwards closed logic, so it has this property that if a team satisfies the formula, then every subteam also satisfies the formula. Good. And then we get some nice complexity results. So what was known before our work was not much. So essentially, we knew that TeamLTL without the splitting disjunction is in p-space, but here the logic without it is quite weak. And then we knew that if we add a contradictory negation, which essentially gives the logic ability to do universal set quantification, essentially, so the dual of the splitting disjunction, then we are in a really high complex logic. So we have a completeness for third order arithmetic, but nothing else was really known between. So what we establish here is that already this extension of TeamLTL with inclusion atoms and Boolean disjunctions is undecidable model checking. But we get these quite large classes of logics that are decidable. So if we take left flat fragment of TeamLTL with any set of downwards closed atoms, then we are decidable. And essentially, what is a left flat property? Well, we restrict until and weak until to these syntactic forms, where essentially the left-hand side is restricted to trace properties. So this is a big restriction, but it still gives quite large expressivity with the logics. For example, we have the future phi for any phi is definable, even though globally phi is not definable for all phi. But essentially the point here is that since this left-hand side of the formula will be evaluated in an arbitrary many places in phi until psi, then by restricting that to be a bit simpler, we can essentially obtain computationally nicely behaved logic where the complexity of team semantic is really on the right hand side of until and weak until. Okay, so where do we get these inclusion results from? Well, the biggest point is here that we show how to translate different logics here with team semantics to prefix classy fragments of these hyperlogics. And if we only have downwards closed atoms and we assume left flatness, then we get to this very small fragment of hyperQPTL. So we just have a block of uniform proportional quantifiers, single trace quantifier, and then LTL formula. And if we don't assume left flatness, then we also need to have this kind of non-uniform proportional quantifier. So it's essentially a true MSO quantifier. And then we get a translation to here. And then if we allow also non-downwards closed atoms, then we require a bit more in the quantification of traces. How do we prove the undecidability then? Well, essentially we give a reduction from non-deterministic 3-counter machines. So a 3-counter machine has 3 kind of instructions. So we have this instruction that says that we add the value of counter A by 1, and then we must go to instruction labeled J1 or J2 non-deterministically. And then we have the same to decrease the value of a counter, and then we have this kind of check whether something is 0, and according to that go to the J1 or J2. So one special thing here is the concept of B-recurring and lossy. So we say that the computation is B-recurring if the instruction label B occurs infinitely often. And the computation is lossy if the counter values kind of non-deterministically decrease. So in principle, in the computation, we have some kind of configuration like this. And in the lossy computation, the values J, K, and L of the counters can decrease without our input, let's say. And then what is known is that deciding whether a given non-deterministic 3-counter machine has a B-recurring computation for a given B is sigma 1 complete, while the same question for lossy B-recurring computations is only sigma 0 complete. So we are then able to prove our undecidability results by reducing these counter machines to model checking problem of our logic. So for the high undecidability, we are able to reduce the existence of a B-recurring computation to a model checking problem of this logic. But if we don't have this universal subtheme quantifier, then we are only able to enforce lossy computations. And the idea of the encoding is here. So essentially we have a set of traces and a time step I. And if we cut away the prefixes before I and just consider the set of traces with postfix starting from I, then we get a set of traces that encodes the value of the counters of the ith configuration. So essentially the value of CA is then the cardinality of this set here. So the cardinality of those T's that have CA true in them. And this is also the reason why we can enforce only lossy computation in this logic. So essentially, when we cut these postfixes, some traces that are distinct in T might collapse to be same in this cut version of the trace set. And essentially, using this universal subtheme quantifier, we can force that these kind of collapses do not happen. And that's the reason why this logic, we get high undecidability, and here we only get undecidability. Okay, so what we have had here is that we have shown what is TeamLTL, and we think that it is a promising purely modal alternative for logics for hyperproperties. So from the expressiveness side, we know that it's uncomparable with HyperLTL. And if we assume left flatness and downwards closure, we get down to this simple prefix fragment of HyperQPTL. And in general, we can get to HyperQPTL plus. And in the complexity side, we found logics or fragments of those that are decidable all in X space if we assume, for example, left flatness and downwards closure. And then we showed on the other side that also relatively simple extensions of TeamLTL are already undecidable. But of course, there's still a lot of work to be done here. So if we take away things here or add things here, can we stretch the decidability barrier upwards or the undecidability barrier downwards? Thanks a lot. And if you are interested more on the details, please check them from our paper, or you can of course also send an email to me or any of my co-authors.